19b. I think Mr. Bergquist said something yesterday about completing the circle. Close to that. Wrong shape. Completing the square. Yeah. So once we did example A, we kind of saw that example B would work that way. But in general, we may not realize that we can borrow from the 10 and ostracize the 1 to make something work. So this is going to be one of our new strategies, completing the square. And typically when we complete the square, we're completing the square for the sole purpose of setting it up for an inverse trig, to set up an inverse trig. Okay, so you look to factor something like that, and it doesn't factor. Now, unless you see right away what the perfect square constant needs to be, you could do it this way. To complete the square, you got to have a couple of things happen first. First of all, of course, you need to have your terms written in descending order of degree, but you also need the leading coefficient of your squared term to be a 1. And it is. Ours is already a 1. If it weren't a 1, you would then have to factor out its coefficient from both your squared term and your non-squared term, and it really wouldn't matter if you did it on the constant, okay? So what we're going to do to complete the square, it's a little bit different maybe than what you did in Algebra 2, where you actually had an equation, and you could just add the same thing to both sides and keep the equation in balance. Here we have an expression that we're working with. So if we want to complete the square, we're going to have to add something right here. Then we're going to have to add the opposite of it on the outside, so that we're really adding a clever form of 0, which doesn't change the value of the expression. So that's what this is here. We're going to add something in the first blank, and then the opposite of that something in the second blank. So what to add? It's always determined by this. Once your coefficient of your leading term is 1, you're going to take half of the middle coefficient, the linear coefficient, take half of it, and then square it. Take half that number and then square it. So half the 6 is 3. 3 squared is 9. Now in this case, because there was nothing factored out to make that coefficient of 1, I really just added a positive 9. So I need to add now the opposite of positive 9, which is negative 9. You'll see in a couple of examples from now maybe when we do have to factor out, if you factored out, let's say, a 2, remember you didn't just add a 9 on the inside, you actually added a 9 times 2, which would be an 18. So you'd have to subtract 18. So that's how you complete the square. With that done now, you can pull the 3 out front. You're left with the 1 there. And, of course, then you've set up a perfect square trinomial. And the way it's going to always factor is the square root of the first term is your first term. The square root of the third term is your second term. And the sign in between the two terms is the sign in between your binomial squared. Of course, hopefully factoring at this level is not going to be difficult for you. And then you can just combine the two that are there. Negative 9 plus 10 is positive 1. And as we already saw yesterday, then, this does set up an arctangent. That's u squared. So u is x plus 3. That's a squared, so a is 1. The derivative of x plus 3 is 1. We're not off by anything. 3 goes along for the ride. We do have a 1 over a in front, but it's 1. So we just go straight to arctangent of u over a, which is x plus 3 over 1, or x plus 3 plus c. So completing the square. Okay, so having done that, let's look at part C. Part C is very similar, except now it's x squared plus 6x plus 8. Does x squared plus 6x plus 8 factor? Not into a binomial squared, but I think it does factor into x plus 4 times x plus 2. Now, is that going to be of any benefit to us right now? Can I split that up and say it's this plus that? Is that? No. There will be a way that that's going to be very helpful later on when we get to a partial fraction decomposition. Okay? But right now, that's not going to be helpful. So maybe we can try it another way. Maybe we can complete the square. Let's try completing the square on this one. X squared plus 6x. Half of 6 is 3. 3 squared is 9. So we'll turn around and subtract 9 plus the 8 that was there to begin with. That gives us 1 over x plus 3 squared again. And now we have negative 9 plus 8, which is minus 1. Is that going to be an arctangent anymore? No, arctangent is something squared plus something squared. That's a minus. The only ones that have minuses are the other two. Oh, could that be one of the other two? No, the other two both have square roots. Can I just take the square root of the top and the square root of the bottom and say now it... No, because that does change the value of an expression, right? Yeah, you can't do that. So this one we can't do yet. Can't do yet. But you could say yet and then whisper again, but I'll be back for you when you least expect it. And we'll get back to it when we learn partial fraction decomposition by the Oliver Heaviside cover-up method. Yeah. Okay, that's page 8 of 11. We got some pages to go still here. Example 20. I'm not going to read all that stuff up there. It says to find the area. When we read the word area, we're thinking what? It's got to be what? Positive or negative? Positive. Never negative. Has to be positive. And who's in charge of making it positive? U is. Right, U is. Okay, so find the area of the region bounded by the graph of that, the x-axis and the lines x equals 3/2, and x equals 9/4. Verify on your calculator if you want to. Okay. All right, so step 1 is to identify the region. All we need to do is sketch that without a calculator. Do you know what that graph looks like? Well, we don't have a calculator. Let's see if we can graph the other ones first. There's the, let's see, in red it says the x-axis. There's the x-axis. And the lines x equals 3/2. I know what that one looks like. That's the vertical line. And x equals 9/4. That's another vertical line. Yay, I got those down. Now, this function here, it's not necessary really to know what the curve looks like, but maybe just realizing that this function over its domain has what types of outputs. The top is always +1, and anything that comes out of the denominator that works will also be positive. So this function is entirely non-negative over the region. So assuming it exists in between 3/2 and 9/4, we should just be able to find the integral, which would represent the area. Let's quickly find the domain, because this is kind of a good review question. We can't divide by 0, and we can't take square roots of negatives, and we're at a risk of doing both of them. But if I say that 3x minus x squared has to be strictly greater than 0, that'll take care of both of them, right? It'll never equal 0, and it'll always be positive. So think about what the graph of that looks like. If you find the x-intercepts by setting it equal to 0, you could factor out your x, and you get 3 minus x. And so it's going to be a parabola that opens down, and it has an x-intercept at 0, and way out here at 3, and it looks like that. So notice that that graph is entirely positive between 0 and 3. So the domain of this function, which could show up maybe as like part A on a free response, would be all the values strictly between 0 and 3. Well, I know that 3/2 is 1.5, so it's going to be okay from 0 to there. 9/4, is that less than 3? Yeah, because 3 would be 12/4. So this does give us kind of a subinterval of the domain, and we know our function's entirely non-negative on that region. So it turns out that the integral will give us the area exactly. It's entirely positive. So here we go. The area will be then the integral from 3/2 to 9/4 of our function, which is 1 over the square root of 3x minus x squared with respect to x. That right there would get a check for the setup more than likely. And all we all have to only do, that didn't come out right, is find the antiderivative. Find the antiderivative. So you would gravitate towards that as your inside function. Its derivative is 3 minus 2x. Are we only off by a constant? No, we're off by a lot. So it's not going to be a power rule. Nothing to split up. Factor it. Is that going to help here? I'm going to have the square root of x times 3 minus x. That's not going to be helpful. I guess inverse trig, if it's going to be anything, right? Inverse trig, It can't be arctangent because it has a radical, right? Does it even look like it's close to an inverse trig? It has to either be like number minus function or function minus number. Number squared minus function squared, or function squared minus number squared. If I do, it would have to be like a square root of x outside the radical because it wouldn't be an x squared that I'd factor out. So unfortunately, that wouldn't help. But what if I completed the square so that I had a function squared maybe plus some number squared? This is one where we do want to complete the square. You got negative x squared, if you just flip that around, plus 3x. Now remember, to complete the square, the coefficient of the squared term needs to be a what? A 1. Is it a 1? It's the opposite of 1. So we need to factor it out first. Now I'm not going to take a whole other line to do that, but if you factor out that negative, you're left with a positive x squared, then a minus 3x. And now you're going to complete the square inside the parentheses. So plus some magical number, close it, and then plus the opposite of that magical number. So in the denominator, under the radical, you're going to complete the square. All right, let's go ahead and do it. What's half of negative 3? Negative 3 halves. And then you square that to get 9/4. Now, did we really just add a 9/4 in the denominator under the radical? No, we added really a negative 9/4 when you distribute. So we need to have the opposite of negative 9/4, which is positive 9/4. Yeah. And very quickly, if you redistribute the negative and combine like terms, you'll see that you get what you started with. Okay, so what that allows us to do then is write the bottom as a perfect square trinomial in the first term. Now, I'm going to have a 9/4 there as my number. I'm just going to go ahead and leave it there. Notice there was no other number there already to combine it with. And then I'm going to be left with minus, and this should factor into the square root of the first term is x, the square root of the last term is 3 halves, and then you take the sign of the middle, which is minus dx. And now you reevaluate it. Now if you look under the radical, you have the square root of a number minus a function squared, which could set up now as an arc, what? Sine, yeah. So if that's a squared, a must be the square root of that, which is 3 halves. And if this whole thing is u squared, then u must be x minus 3 halves. So let's check. What's the derivative of what we're calling u? 1. That's what we have in the numerator. So we're not off by anything. And I'm running out of room. Let me shrink this down. And so we're ready to go. We're not off by anything. So we have no correction to make. The only rider is a 1. So the only real question is, do we have a 1 over a in front on this one? Yes or no? No, it's arc sine. So it goes straight to arc sine of u over a. Well, that's going to be x minus 3 halves all over 3 halves. Do we need a plus c? No. We're going to evaluate it from 3 halves to 9/4. Now, here's what you could do. You have two options. Before you evaluate it, you can realize that you can stay, change, flip, and distribute the 2, or multiply by 2 over 2 and get rid of the complex fraction. But notice we're evaluating it from 3 halves to 9/4. It might actually be easier to leave it in that ugly form as we evaluate it and maybe clean up an answer at the end. It's entirely up to you. But I'm noticing when I plug in my lower bound, I'm going to get a 0 in the denominator if I leave it as is. So let's evaluate it. Plug in the top, and I get arc sine of, let's see, 9/4 minus 3 halves, where 3 halves is the same as 6/4. So 9/4 minus 6/4 is 3/4. So I'll get 3/4 divided by 3 halves, which is the same as multiplying by 2/3. So that'll be the first one, dividing by 3 halves, stay, change, flip, 2/3. Minus, when I plug in the bottom, I'm going to get arc sine of 0 over 3 halves, which is 0. Now, is that a numerical answer? Good place to stop? Pre-response? Yeah, I think so. But let's keep going then. Arc sine of, your 3's divide out, you get 2/4, which is a half, minus arc sine of 0. It's another good place to stop. But let's evaluate it now. Sine of what angle is 1/2? Arc sine of 1/2 is what angle? Pi 6, good. And again, it's not 5 pi 6, even though sine of 5 pi 6 is a half, because that's outside the principal value range, the inverse sine function. And then arc sine of 0, where is sine 0? At 0. And we don't include pi, because again, it's outside the PVR. So the final answer is pi 6. So there you go, completing the square to set up an inverse trig. Let's see if the calculator is as smart as we. I don't think so, because I don't think it's going to get pi 6, which is exact. But it might get the decimal equivalent. By the way, pi 6 is equal to that one right there, 0.523. Now, just to review, areas on a calculator, like if we hadn't thought about maybe whether or not our function was entirely positive on the interval, we could just say math 9. And then, of course, we would go from 3 halves to 9/4. And what could we do to our integrand just to make sure that it was non-negative over the region? Absolute value. Math number 1. And then we get 1 divided by the square root of 3x minus x squared. Of course, it happens to already be positive, so taking the absolute value of it is not a big deal. But remember, this is how we find areas on our calculator, and we would actually have that written on our paper. And if we did it right, if the calculator's smart, we should get the same answer, at least to the third decimal. In this case, more than that. Way to go, calculator. Not so bad. And if you hit math, enter, enter, of course, you'll get the same answer. Yeah. Now, if you suspect that there's a pi in there somewhere, maybe you could divide out a pi, maybe, and then hit math, enter, enter, and then multiply pi back in, and then hit math, enter, enter. And it still doesn't convert it to pi 6, but maybe, I don't know, you can figure that out. Okay, cool. Completing the square. Leading coefficient of your square term has to be a positive 1. All right, time for yet another algebraic strategy besides splitting up terms, factoring, expanding. This one here. Okay, we have a quotient. Is there a quotient rule for the integration? No. I didn't wait for you to answer. Sorry. Is there a quotient rule? No. No. Good. You would hopefully gravitate to the bottom as being your inside function. Is the derivative of x squared plus 1 x squared plus x plus 1? No, not quite. Not quite. So that's not going to work. Can we split up terms? Do these divide out and those divide out? It's x. Is that a strategy? No. Yeah, I guess. Yeah, if you're a comedian, that's the strategy. Right? Some people might find that funny. Some people not so funny. What can we do? We could split it up. You could take any term in the top and put it over the entire denominator, or any combination of terms, not times, plus, any combination of terms over the entire denominator. So this is not a bad thing to do, and it might be helpful. Would it be helpful? That third term is looking mighty fine. That looks kind of like a what now? Cheeseburger, also known as arctangent. Good. This one is looking mighty fine. Looks like a big old bag of French fries, also known as a natural log with the correction of a half. But this one is still problematic. Milkshake, right? Which is bad for you. So what we're going to have to do on this one, the strategy that I'm going to give you, is something that is probably best done in the beginning anyway, So even if you could do it on this line, you're going to have to carry around that other stuff after the fact. So let's talk about what we could do either on this one when the degrees are the same or on that one. Any idea? Lean in and listen to what that right there is actually telling you to do. Divide me, please. Well, you could use synthetic division if you're dividing by a linear factor, but we have a irreducible quadratic factor, and it doesn't work with that. So long division is a little bit better opportunity in general, and that's going to be a new strategy. When does long division work? When you're doing it. Because y'all are awesome at it. No, it's when the degree of the numerator is greater than or equal to the degree of the denominator. It works all the time, really, even if the numerator is smaller, but you're going to start generating fractions, and we don't want to do that. So it's a good strategy, I should say, whenever the degree of the numerator is greater than or equal to the degree of the denominator. Something can go into something else that's the same size or larger. So let's go ahead and do long division. I know you remember how to do it, but just be patient and see if I do. The numerator is the dividend, which means it goes inside the house in descending order. And the denominator is the divisor, which means it goes outside the house. It's not so critical to have a placeholder for missing variables, but you can if you want. It is kind of nice to have them written in descending order of degree. So the way you do that is you just look at the first terms in each first, and you ask yourself, how many times does x squared go into x squared? That is, what is x squared divided by x squared? And the answer is 1. And you put it right above that x squared. Now you distribute, remember, to both of those. That's how you get the other terms in the divisor involved, and you get x squared. So at this point, those should be the same. If not, go back and try step 1 again more correctly. And then you get plus 1. So I'm going to write the plus 1 underneath the like term over there. And then we subtract. So we have to change both signs. Don't forget to do that. So you get a 0 in the first one. There's nothing to bring down, subtract there, so it's really a 0. X plus 0 or x minus 0 is still x, and 1 minus 1 is 0. So at this point, you could have another constant, but you don't. Now, does x squared go into x to the first? No. So we're done with the problem. So you box it and go on to the next. Have we BOTC'd yet? No, we're done with the long division. But why does it work? You can write the result of your long division, which would redefine the original problem as your quotient, Q, which is 1, plus your remainder. This is your remainder over the original divisor or your denominator. So for us, that means we can rewrite the original problem as 1 plus x over x squared plus 1. And there you go. It's the exact same problem. So notice now, instead of splitting it up in the beginning, where we had 3 terms, the second 2, both of being which we recognized, we only have 2 terms. It's actually going to be less work. Do we already know what the first term is, the antiderivative of 1? It's x, wow. And then this one, is that an arctangent? No, because your inside function is x squared plus 1, and its derivative is 2x, which is the numerator except off by a 2, so you'll have a correction of a half, and it becomes a what rule of integration? Natural log. Do we need the absolute values here? X squared plus 1 is always positive. Doesn't hurt to have them, but don't need them. And you're done. It's that easy. So whenever you have the opportunity to long division, it's probably easier to do it on the front end of the problem instead of splitting it up and using that other strategy. You'll still get the same answer, but you'll have more work to do. Things will cancel, and you'll end up with the same answer. All right, so when did long division become a new strategy? When the degree of the numerator is greater than or equal to the degree of the denominator. Letter B. Okay, let's see. The derivative of the top is 3x squared minus 6x. Is that going to be x squared plus 3 or a multiple of it? Would that work anyway? No, because the derivative at the top might generate a quadratic, but it sure doesn't generate 1 over a quadratic, so that would be the total wrong way to go. You would maybe look to that first, and the derivative of this generates a derivative in the numerator, which is not going to make the degree any bigger, so not a good thing. We could split it up. We can put that over that, plus that over that, plus that over that, plus that over that. Or maybe just realize that we have a degree in the top that's larger than the degree of the denominator, and what's it called? Short division. Yeah. You'll make short work of long division. All right, so x cubed minus 3x squared plus 4x minus 9. And then x squared plus 3. All right, x squared goes to the x cubed how many times? Well, it goes in one time being 1x time, right? So it's really x cubed over x squared, which simplifies to x. That's what you're doing. You're basically looking at those leading terms. So it goes in x times, really. And now when you distribute, you get x cubed. Those should be the same. Minus 3x. Notice I'm going to put that minus 3x over here underneath the like term. Now we got to change both signs. Don't forget to change the signs, especially of that second one. It becomes plus now. I sure did. Way to go, me. Yeah. It becomes plus 3x, which becomes minus. Sometimes there's such thing as too efficient. So negative 3x squared is going to come down, and I get a plus x. Thank you. And then this minus 9 comes down. And we look to do it again. Does x squared go into a negative 3x squared? Yes, it goes in negative 3 times. And again, you can just go off to the side and say it's negative 3x squared over x squared, negative 3. And when you distribute, you get negative 3x squared. I'm not going to be too efficient this time. I will get a negative 9 when I multiply, writing it into the like terms. Now I'll change both signs because I haven't already just changed one. That goes to 0 for sure. It should. Just conveniently, the last term goes to 0. It doesn't have to. And then we just bring down the positive x. And we look to do it one more time. Does x squared go into x? No. So we're done with the long division. Now that means we can write the original problem as the quotient, x minus 3, plus the remainder, x, over x squared plus 3. Now we have 3 terms. The first 2 are a piece of cake. Integrating from left to right, we get 1/2 x squared minus 3x. And the last piece, we're off by a 2, so we have a correction of a 1/2, and it becomes a natural log rule. Again, no absolute values required. Long division, another bona fide strategy. We'll do long division again later on when we learn partial fraction decomposition by the Oliver Heaviside cover-up method. It's going to be one of those things we look for first automatically. Yes, Oliver Heaviside. Ironically, a very thin fella. Heaviside was not his middle name. Cover-up method was not his last name. His last name was Heaviside. He was a bike enthusiast. He liked to invent types of bicycles, and he was a big fan of the spoon brake. I think he might have invented the spoon brake until he crashed because the spoon brake failed and he severely injured himself. Spoon brake broke. Yeah, brakes aren't supposed to break right in the middle of braking. Here are some Triggy ones. Ready? Fine. Now we've done one like this. Sine of x times cosine of x. Anyone? Anyone? What to do? How to proceed? Long division? Nope. What? In terms of sine and cosine. Factor it. Guess and check. Yeah. Plus C. Yeah, that's some weird symbol. Good thing an administrator didn't walk in. I think I'm part of some math gang. Which one would be the inside function? We've seen this one already. Either cosine is inside something to the first and you're off by a negative, or sine is in something to the first and you're off by a nothing. And you're off by nothing. So which one would you want to use? I would like to be off by nothing. So I'll let sine of x be inside something to the first. Its derivative is cosine, and then the rule of integration would be it's Friday. It's Friday. Plus c. And you're done. You could call it sine squared of x over 2 plus c. That works. And remember, the other version would generate it in terms of cosine squared, but by the Papa Pig, you could show that you're only off by a constant. That's one way to do it. That's probably the easiest way to do it. But there is another way. I don't know if anyone thought about doing this. Multiplying by a half out front and multiplying by 2 on the inside. Anyone think about doing it that way? What did I do? I just cleverly multiplied by 1. Why would I do that? So that I can call that what? Sine of 2x. Now it becomes a pattern recognition. Now my inside function is 2x. What's its derivative? 2. Do I have a 2? Nope, but I'm only off by a 2, so the 1/2 goes along for the ride, and I have a correction of another 1/2. And what's the antiderivative of sine of blob? Negative cosine of the blob. Yeah, plus c. And so that's negative 1/4 of cosine of 2x. And of course, you could show that that's equivalent to the others by using the double angle identity for cosine of 2x, which is cosine squared minus sine squared. All right, so that one only worked to both ways with the sine of cosine because they were both to the first power. How about this one? Does this one work both ways? Could cosine be the inside function? What's its derivative? Sine squared? I don't think so. But sine could be the inside function, again, because it's inside something squared. And what's the derivative of sine? Cosine. Are we off by anything? No. So what's the rule of integration? Well, it's blob squared, so it becomes blob cubed plus c. Pattern recognition. Lickety split fast. All right, letter C. Sine squared. Ooh. 1/3 sine cubed? Almost. If only there were a cosine out there somewhere. Make one. Multiply by cosine over cosine, which is 1. It goes away. Yeah. No. This is a good one. You're going to have to use an identity here. You're going to have to use the power reducing identities. Okay, so here they are. Sine squared of x is equal to 1/2 1 minus cosine of 2x, and cosine squared of x is equal to 1/2 1 plus cosine of 2x. Those you have to memorize, or rememorize, or still know. Don't forget them. So when you're integrating just particular powers of sine squared, or just sine squared and cosine squared, you have to use those. You will know how to do this after we cover the section on polar area. Trust me. But right now, we're just kind of seeing what it looks like. So 1/2 I can pull out front. Sine squared becomes 1 minus cosine of 2x. And now I have two terms. Each of them look like they're going to be pretty easy to do. Just be careful with the 1/2 because it will need to be multiplied by both of the terms in the antiderivative. You get x, and then of course cosine has an inside function of 2x, which will generate an unwanted 2. So then you're going to have a correction of a 1/2. And what's the antiderivative of cosine? I have the negative there, so what's the antiderivative of cosine? Regular sine. Good. So it's sine of 2x. And then plus c. And then distribute if you want. So the power reducing identity makes that possible. Just like the letter C sometimes makes Sesame Street possible. That's on HBO now. Did y'all know that? It's on HBO. Sesame Street is on HBO. It's a 30-minute program. I watched it the other day, the whole episode. I learned something. They did stop censoring it, and apparently when Bert gets mad, he's got some foul language that they're not editing out anymore. Big Bird doesn't wear feathers on HBO. Oh, foul language. Yeah. No. Bert doesn't cuss. Big Bird wears feathers. But the show, it's updated. Yeah, it's kind of updated. It's kind of interesting. Hey, sine cubed. Sine cubed. 1/4 sine to the fourth? No. Power reducing identity. Is there one for the cubes? Not that I know of. What can we do? Any ideas? What? How? Factor out one sine. Factor it, yeah. Hey, nice. Good idea. Now the derivative of that one's that one, or that one's that one? No. Reduce the power. Oh, I could. I could use the power reducing identity right here, but that's going to change that angle to a 2x and keep that one as a 1x, and that is not good.
My kids want to know if you have a minute left in the class, you come over and do the ghost pepper challenge.
What is the ghost pepper challenge?
1 minute on your worksheet that you have online.
Oh. Yeah. Like to do 10 of them in 1 minute?
Yeah.
Like from the unit circle? Yeah. Oh. Ghost pepper challenge. I can't do the ghost pepper challenge.
Well, I did it. And
you got it done in a minute?
No, I did it in a minute and 40, and a kid made an alarm go off about 30 seconds into it, and I freaked out. Like, it's already been a minute.
Yeah, and I'm supposed to come trust your class?
Well, I can make it.
They're going to try and sabotage.
Okay. Well, if you're up for the challenge,
okay.
They're ready to be wowed.
Right, yeah, right now?
Well,
okay, all right. Okay, we'll see. All right, so what do we do next? The derivative of sine is not sine, so that's not going to work. And the power reducing identity is going to take the angles away from each other, which means that we're not going to be able to compare the two factors to each other anymore as the derivative of one being the other. Papa Pid's the way to go. Very good. So I call this the odd man out rule, where you have like an odd power. You're going to take one out, like Berquist said, and you're going to convert the other one, which should be an even power, using Papa Pid, and you're going to get that, 1 minus cosine squared. Now you're kind of still not really able to do much until you distribute. You get sine of x minus sine of x times cosine squared, which I'm going to write like that. Once you distribute now, you have two terms, and each term becomes pretty easy to do. The first term is sine. What's the antiderivative of sine? Negative cosine. Good, negative cosine. And then the second one is pattern recognition, or u sub. Cosine's your inside function now, and its derivative is? Hi. Negative sine. So if you want, you can let that negative get packaged back up and make that a plus. And then blob squared becomes what? 1/3 blob cubed. Yeah, cosine and then plus c. There you go. Odd man out. It works with odd powers of sine or odd powers of cosine as well, by way of Papa Pid. And there's a lot more interesting sine or trig examples to come, or not necessarily in BC calculus, but there's trig substitution. There are other advanced methods with powers of sine and cosine. There's a whole category of powers of sine and cosine. Okay, here's a simple one serving as a confidence booster. And a segue. There it is. Segue. I don't know why I put a Q. Okay. Maybe it's a sequence. Yeah, maybe. A sequence of ellipsis points. No, a sequence of ellipsis points would be more like that. Anyway. All right, here we go. Ready, set, go. What's the inside function? 2x minus 1. What's its derivative? 2. Are we off by just a constant? Multiple? Yeah. So we have a correction of 1/2. Yahoo. So whenever your inside function is linear, you're not going to see another variable factor. You're only going to see one variable integrand factor. But because the inside function is linear, you're going to be off by a constant more than likely, which you can easily correct. So this is the same as blob to the 1/2. So without rewriting it, we get blob to the 1/2 plus 1, which is 3/2 with a 2/3 in front. It's reciprocal, and then plus c. Are we done? I'm not. Don't forget to write the blob in there, 2x minus 1. There you go. Now you're done. And simplify if you want to. So that wasn't too bad. So that's the integral of the square root of 2x minus 1 with respect to x. Letter 23, 4, number. I need to watch more Sesame Street. All right. The integral of, is that the same problem? It sure looks the same. No, what's the difference about it? I don't know if I should try any ghost pepper challenge today. It's not working. It's not working. There's an x there on this one. This one has an x and the previous one did not. Are we going to do it the same way? I don't know. Let's see. What's the derivative of 2x minus 1 this time? Still a 2. Oh, shucks. We're off by an x. So it's not going to just be a power rule. We've had some strategies already. Power reducing formula? No, that's not, no. Split up the terms. We can put them both over 1. Complete the square? Do we even? No, we don't even have a quadratic into it. What else? Factor. It's already factored. Expand. Add a clever form of 0. 0 over 0.
Teachers, please pardon this interruption.
Nothing we can do.
Student council members, there will be a meeting Monday after school in the library.
And at this time, please turn to TV channel 4 for the morning announcements, or you can view them on your iPads at nbhstv.com.
There you go. So u-sub has been something that we've had the option to use all along, but pattern recognition is a little more efficient. This is one of the times where u-substitution is actually kind of needed. When our inside function is linear, that means degree 1. In this case, it's 2x to the first minus 1. Or smaller, like it could be x to the 1/2 or x to the 2/3, as long as the degree is 1 or smaller. And you find that you are quote-unquote off. I didn't put them there, but you know what that means, right? If you're off by more than a constant multiple, use u-substitution. So here's what it looks like. We're going to still let u equal 2x minus 1. And if you want to kind of get a running total over here, what we're going to have then is instead of the square root of 2x minus 1, we're going to have the square root of u. And all we have left to replace then is the x and the dx. Now, up to now, when I've taken the derivative of both sides with respect to x in differential form, I've been able to replace that other variable factor and the dx with a single substitution. But notice the derivative now, the derivative of u is just 2 dx. I don't get the x, which is why I'm having to do this method to begin with. So I'm going to have to substitute now, not as a group, but I'm going to have to substitute individually the x and the dx. So let's solve that for dx. 1/2 du then is going to equal to dx, and now I can put that 1/2 in front, and I can put the du at the back. But what's still left to substitute? X, right? And this is why it's helpful when it's linear or smaller. That equation there, because it's linear, real easy to solve for x. And that's what you have to do. I'm going to add 1 to both sides. And instead of dividing both sides by 2, I'm just going to multiply both sides by 1/2. So I get 1/2 u plus 1. And so I'm going to plug that in for x. Now the 1/2 as a constant multiple, it can come out front with the other 1/2. And then the u plus 1 I can just put in there as another factor, in front of the du. So I end up with 1/4 the integral of u to the 1/2 times u plus 1 du. Now notice I still have a factor, or two factors in my integrand. And the derivative of u plus 1, which is inside something to the first, is 1, not u to the 1/2. And u, which is inside something to the 1/2, is 1, not u plus 1. So it doesn't appear like I'm any better off, but I am. Simply because up here, notice the binomial had the radical around it, which is to the 1/2 power, and there's nothing we can do. We can't distribute the x into the radical unless we make it x squared, and then we can't do anything. But by letting the ugly exponent factor become the single variable, look what it does. It flip-flops them around. And now I have u to the 1/2 times u plus 1, which means now I can do what with this little singular unit? I can distribute. And so after you do u-substitution, bless you, when you're off by a more than a constant multiple and your instead function is linear, the next step is always going to be to expand. X game style. Expand. So you get 1/4, and then if you distribute, you're going to get u to the 3/2 plus u to the 1/2. Now notice we haven't BOTC'd yet, but that comes next. So we're able to expand, whereas in the previous original version, we could not. That's what the u-substitution does. It flips them around. Okay, so here we go. 1/4 goes along for the ride. U to the 3/2 becomes u to the 3/2 plus 1 is 5/2. Now, if you want, you could do something else on this line. Instead of calling it u, you could leave parentheses there and then come back and plug it back in. It's going to require another line of writing otherwise, but I'll do it that way for the first time here. U to the 1/2 becomes u to the 3/2 with the 2/3 there, and it's an indefinite integral, so we need to put plus c. Can I stop there for an indefinite integral with u-sub? No. If it were a definite integral and I had changed my intervals of integration from x's to u's, then I could have plugged in and evaluated it in terms of u. But I do have to plug back in. What is u? 2x minus 1. So you get 1/4, 2/5, 2x minus 1 to the 5/2 plus 2/3 times 2x minus 1 to the 3/2 plus c. Now you know what problems like this are replete with opportunities to do? Once we get to the right answer, which of course is this. Factor out least powers. Yeah, let's review that. Hody hi.
I know. That's all right.
No, it works. Yeah, let's factor out your 2x minus 1 to the what power? Which the exponent's the smaller, 5/2 or 3/2? 3/2, yeah. Now you could also factor out like a 1/15 if you want, which would be like the LCM of the two fractions denominators. That's going to leave us with a 2/5 and then a what? A 2x minus 1 to the what? Remember, we divide out, you factor out, you divide out, you subtract the exponents. 5/2 minus 3/2 is 2/2, which is 1, so you're left with that, and then plus 2/3 plus c. Let's go ahead and factor out a 1/15 while we're at it, maybe as a second step. Why 1/15? Because 15 is the LCM of 5 and 3. If I factor out a 1/15 and combine it with the 1/4, the 15th times a 4th is 1/60th. 2x minus 1 to the 3/2. Now this is kind of fun too. When I factor out a 1/15, I'm dividing by 1/15. Dividing by 1/15 is the same as multiplying by its reciprocal, 15. So 15 divided by 5 is 3 times 2 is 6. So you're left with 6 times 2x minus 1. By factoring out the LCM, you're left with no fractions in there. And again, if you're not sure, just redistribute the 1/15, then you get 6/15, which is 2/5. Plus, factoring out a 1/15 from 2/3 is the same as 2/3 divided by 1/15, which is 2/3 times 15. 15/3 is 5 times 2 is 10. And what that allows you to do essentially is have a relatively nice little polynomial in there. That simplifies to 12x, and then minus 6 plus 10 makes it plus 4. And now you can factor out a 4. You said it, not me. But yeah, you can. And then, of course, 4/60ths would put it back as 15. I guess, yeah. We could have factored out a 2, I guess. Yeah. I was focusing on the denominator, so I kind of forgot. But yeah, there's a 2. But anyway, this is just more fun to have 1/15, 2x minus 1 to the 3 halves times 3x plus 1 plus c. Plus c each time plus c. Yeah, there you go. So kind of neat. So when is u-substitution actually required? When your inside function is linear or smaller, and you're off by more than a constant multiple. And you're going to have to replace, of course, the thing you're calling u, you're going to have to replace dx and the variable x separately. And then the next step after that is always going to be to expand X game style. Challenge. You want to go ahead and do that? I don't want to do it. Do y'all want to do that? I don't want to. We'll stop at 24a then. I was going to finish the notes today. Okay, we still have another page.